Hi all. In previous class, we discussed about introduction of chemical engineering thermodynamics to review on first and second laws of thermodynamics, fundamental property relation for closed system and open system. In today's session, we will discuss about chemical potential and partial properties for binary solutions. Now coming to chemical potential. Chemical potential is defined as the partial differential of the Gibbs function of the system with respect to number of moles of the substance. Chemical potential is defined as the partial differential of the Gibbs function of the system with respect to number of moles of the substance. Chemical potential is also known as partial molar Gibbs free energy. Mathematically, chemical potential is expressed as mu I is equals to dou of Ng by dou Ni at constant temperature, pressure and number of moles. Chemical potential is denoted with mu. Mu I is equals to dou of Ng by dou Ni at P comma T and number of moles. Now coming to chemical potential as a phase equilibrium. Here consider one closed system. See here, consider one closed system which consisting of two phases, that is alpha phase and beta phase. Each phase acts as an open system. Since the mass transfer will occur between the two phases in a closed system, as the energy change will also occur with respect to fundamental property relation related to chemical potential can be applied to each system. Can be applied to each system. Therefore, we can develop individual equations for both phases. That means for alpha phase and beta phase. What is the fundamental property relation? D of Mg is equals to NVdP minus NSdT plus mu I into dNi. This is the fundamental property relation for an open system. Now apply fundamental property relation for alpha phase. D of Ng power alpha is equals to Nv power alpha into dP minus Ns alpha dt plus sigma mu I alpha into dNi alpha, which is indicated as equation 1. Similarly, we apply fundamental property relation for phase beta. D of Ng beta is equals to Nv power beta is dP minus D of Ng power beta is equals to Nv power beta into dP minus D of Ng power beta is equals to Nv power beta dP minus Ns beta dt plus sigma mu I beta into dNi beta, which is indicated with equation 2. Now adding equations 1 and 2. After adding, we will get d of Ng power alpha plus d of Ng power beta is equals to Nv power alpha dP minus Ns power alpha into dt plus sigma I alpha dNi plus Nv power beta into dP minus Ns beta dt plus sigma mu I beta dNi. Now eliminate the terms dP dt terms. D of Ng power alpha plus Ng power beta is equals to Nv alpha plus Nv beta into dP minus ns alpha plus ns beta into dt plus sigma mu I alpha dni plus mu I beta dni, which is indicated with equation 3. Now coming to total property. Total property is expressed in the form of nm is equals to nm power alpha plus nm power beta, which is indicated with equation 4. Then compare equations 3 and 4. After comparison, we will get d of ng is equals to nvdp minus nsdt plus sigma mu I alpha dni alpha plus mu I beta dni beta. After comparison of equation 3 with 4, d of ng is equals to nvdp minus nsdt plus sigma mu I dni power alpha plus sigma mu I beta into dni beta, which is indicated with equation 5. Here, nv power alpha plus nv power beta is equals to nv. Similarly, ns power alpha plus ns power beta is equals to ns, which is coming from total property. Now coming to closed system. For closed system, fundamental property relation is equals to d of ng is equals to nvdp minus ns dt, which is indicated with equation 6. Now coming to closed system. For closed system, fundamental property relation d of ng is equals to nvdp minus ns dt, which is indicated with equation 6. Substitute equation 6 in equation 5. Then we will get d of ng is equals to d of ng plus sigma mu I alpha dni alpha plus sigma mu I beta dni beta. Both sides of this equation d of ng term gets cancelled. Then sigma mu I power alpha into dni alpha is equals to minus sigma mu I beta dni beta, which is indicated with equation 7. Now consider a closed system. For closed system, change in number of moles is equals to 0. That means dni is equals to 0. For closed system, total number of moles is equals to number of individual moles. That is, ni is equals to ni power alpha plus ni power beta. Therefore, ni power alpha is equals to minus ni power beta. Here, ni term goes to 0, which is indicated with equation 8. Now substitute equation 8 in equation 7 in place of dni beta with minus dni power alpha. Therefore, sigma mu I alpha dni alpha is equals to minus sigma mu I beta into minus dni power alpha. Both sides we have to cancel dni alpha term. Therefore, sigma mu I power alpha is equals to sigma mu I power beta. Taking the mu I beta term into this side, therefore sigma mu I power alpha minus mu I power beta is equals to 0. Finally, mu I power alpha is equals to mu I power beta, which means chemical potential in alpha phase is equals to chemical potential in beta phase. Therefore, chemical potential in alpha phase is equals to chemical potential in beta phase. Now, suppose consider pi number of phases. In all pi number of phases, chemical potential is equal, which is indicated with mu I power alpha is equals to mu I power beta is equals to mu I power pi. In each case, chemical potential is equal. Therefore, consider a multiple phases. All are at uniform temperature and pressure and are in equilibrium. When the chemical potential of each species is same in all the phases. Therefore, chemical potential in each phase is equal. Therefore, for multiple phases, all phases are in equilibrium at same temperature and pressure when the chemical potential of each species is same in all phases. This is the conclusion of chemical potential as phase equilibrium. Finally, chemical potential is defined as change in Gibbs energy with respect to number of moles at constant temperature, pressure and number of moles. Coming to next topic, partial properties. Partial properties is defined as change in total property of the solution with respect to change in moles of components of all species at constant temperature and pressure. It is defined as change in total property of solution with respect to change in moles of components of all species at constant temperature and pressure. Mathematically, partial properties expressed as mi bar is equals to dou of nm by dou ni at constant temperature, pressure and nj. Mathematically, partial properties are expressed as mi bar is equals to dou of nm by dou ni at constant temperature, pressure and number of moles. Similarly, partial molar Gibbs free energy is given by Gi bar is equals to dou of Ng by dou Ni. Here, compare equations Mi bar is equals to dou of Nm by dou Ni with Gi bar is equals to dou of Ng by dou Ni. Therefore, Gi bar is equals to mu I. Therefore, partial molar Gibbs free energy is equals to chemical potential. Now coming to relation between molar properties and partial molar properties. Here, consider a system which is function of temperature, pressure and number of moles. Nm is equals to function of temperature, pressure and number of moles. Here, taking the differential on both sides and differentiate with respect to temperature, pressure and number of moles. d of Nm is equals to dou m by dou t into dt plus dou m by dou p into dp plus dou m by dou n into dni. Here, n indicates all mole numbers are held constant. Similarly, nj indicates that all mole numbers except ni are held constant. Here, m into dn plus n dm is equals to dou m by dou t into dt plus dou m by dou p into dp plus mi bar into dni. Here, m into dn plus n into dm. Here, applying differential for nm. Then we will get mdn plus ndm is equals to dou m by dou t dt plus dou m by dou p dp plus sigma mi bar dni. We know that individual number of moles is equals to total number of moles multiplied with individual mole fraction, that is Ni is equals to N into Xi. taking the differential on both sides of this equation, then we get dni is equals to n dxi plus xi dn, which is indicated with 2. Now substitute equation 2 in 1. Then we get m dn plus n dm is equals to n dou m by dou t into dt plus n dou m by dou p into dp plus sigma mi bar into n dxi plus xi dn. After eliminating the terms, dn terms and n terms. After eliminating dn terms and n terms, m minus xi sigma mi bar dn is equals to n into dou m by dou t into dt plus dou m by dou p into dp plus sigma mi bar dxi minus dm. Here, individual terms are 0 as dn terms and n terms are not equal to 0. Therefore, dou m by dou t plus dt. Therefore, dou m by dou t into dt plus dou m by dou p into dp plus sigma mi bar dxi minus dm is equals to 0. Then we know the summability relation. M is equals to sigma mi bar xi. Now taking the differential on both sides of the summability equation, dm is equals to sigma mi bar dxi plus sigma xi dmi bar, which is indicated with equation 4. Now substitute equation 4 in 3. We get dou m by dou t into dt plus dou m by dou p into dp plus sigma xi dmi bar is equals to 0, which is indicated with equation 5. This equation is called as Gibbs-Johann equation. Gibbs-Johann equation at constant temperature and pressure. Now equation 5 becomes to sigma xi dmi bar is equals to 0. Now coming to partial properties for binary solutions. Here consider m is equals to sigma mi bar xi, which is indicated with equation 1. Equation 1 is called as summability relation. Individually, which is applied for binary solutions, m is equals to m1 bar x1 plus m2 bar x2. Here we apply differential on both sides of the equation. Therefore, dm is equals to m1 bar dx1 plus m2 bar dx2 plus x1 dm1 bar plus x2 dm2 bar, which is indicated with equation 2. Therefore, sigma xi dmi bar is equals to 0, which is indicated with equation 3. Now substitute equation 3 in 2. Now for binary system, total number of moles is equals to 1. That is x1 plus x2 is equals to 1. Taking the differential on both sides. dx1 plus dx2 is equals to 0. Therefore dx1 is equals to minus dx2. Then substitute this dx1 with minus dx2 in equation 3. Therefore, dm is equals to m1 bar dx1 minus m2 bar dx1. Then eliminate the term dx1 and taking the right hand side of the equation, dm by dx1 is equals to m1 bar minus m2 bar, which is indicated with equation 4. Now eliminate the term m2 bar. Therefore, m2 bar is equals to m1 bar minus dm by dx1, which is indicated with equation 5. Then substitute equation 5 in equation 1. Then we will get m is equals to m1 bar minus dm by dx1 into x2. Now eliminate the terms m1 and x1. Then we will get m1 bar is equals to m plus dm by dx1 into 1 minus x1. Therefore, m1 bar is equals to m plus dm by dx1 into x2. Here, 1 minus x1 is replaced with x2, which is indicated with equation 6. Which is indicated with equation 6. Then m is equals to m1 bar minus dm by dx1 into x2. Therefore, substitute equation 6 in equation 1. Then m1 bar x1 plus m2 bar x2 is equals to m. Here, m x1 plus dm by dx1 into x1 x2 plus m2 bar x2 is equals to m. Then eliminate the term m2 bar. Therefore, m2 bar is equals to m minus dm by dx1 into x1. Here, m2 bar means partial property of species 2. M1 bar is the partial property of species 1. Here M is the total property. Now coming to conclusions of this session. First, definition of chemical potential. Chemical potential is defined as change in Gibbs energy of the system with respect to change in number of moles of the system at constant temperature, pressure and number of moles, which is mathematically expressed as mu is equals to dou n g by dou ni at constant temperature, pressure and number of moles. Then coming to chemical potential as a phase equilibrium. Here consider a closed system which is divided into two phases. All phases are at uniform temperature and pressure and at equilibrium. Then we have to write the fundamental property relation for both phases. Finally, we assume pi number of phases. In each phase, chemical potential is equal. Then coming to definition of the partial properties. Partial properties is defined as change in total property of the system with respect to number of moles, which is mathematically expressed as mi bar is equals to dou nm by dou ni at constant temperature, pressure nj. Then, in place of m, replace with Gibbs energy. Therefore, partial molar Gibbs energy is equals to chemical potential. Then coming to partial properties for binary system. Here assume a binary system. Here partial properties m1 bar and m2 bar are derived. The expression for m1 bar is equals to m plus dm by dx1 into x2 and m2 bar is equals to m plus dm by dx1 into x2. M1 bar is equals to m plus dm by dx1 into x2 and m2 bar is equals to m minus dm by dx1 into x1. Thank you.